like to talk about errors and error analysis and things that you probably hadn't thought about in high school. That is, in high school, if you did any labs, you probably did some things and plugged some numbers in some formulas and got an answer, and you thought you were done. And unfortunately, you're only halfway there. And so what I want to talk about is, first of all, how to process your data to get an answer, and also then after how to report the answer, and how to, in a sense, evaluate the answer. That is, the quality of the answer, the accuracy of the answer. So this is the part that you haven't done before, I suspect, and is very important. So we're going to emphasize this throughout the year in these introductory labs. Errors. To err is human, they say, yes, but errors here are not mistakes. Mistakes are mistakes. Errors are uncertainties in measured quantities. That error is short for that. So whenever I say error from now on, to save a lot of words, I'm talking about uncertainties in measured quantities. There are two kinds of errors in general. The first one I want to talk about is an error that you have to look hard to find sometimes. It's called a systematic error. They're always the same. The good news is about these is if you can figure out what they are, you can correct for them, and it's a nice constant correction. But if you don't know what they are, you don't even know if you have them, then you have a problem. One systematic error that I noticed many years ago, my sister bought me a tire gauge, which was really nice. And one day I was using it to check the air in my tires, air pressure, and it slipped out of my hand and it fell onto the concrete. I can still see it falling, that split second, and saying, oh no, this is not good. And when it hit the ground, hit the cement, I picked it up and it read 2 psi. Well, I checked this out because I wanted to be able to still use it, and I used it by adding, I should say by subtracting 2 psi from every reading I took with my air pressure gauge from then on. So if it read 34, I really only had 32 because I have to subtract 2 psi. So I did check it, and it is calibrated. If I just subtract 2 psi, pounds per square inch, from the value, it reads very nicely. So that's a systematic error which I discovered, I created, and I can compensate for it and still use it. Another systematic error, which is kind of interesting, I bought a bunch of these meter sticks, and I looked at the meter sticks, and they're actually more than a meter long. They're about 3 millimeters longer than a meter. So if you use a meter stick from end to end, you're not measuring correctly. You're measuring, you're underestimating by 3 millimeters. 3 millimeters out of 1,000 millimeters is only 0.3%. So if you're measuring using a large part of the meter stick, you can probably ignore 0.3%, probably. Sometimes you can't. But the best way to use any meter stick like this is to measure from one place to another place on the scale and subtract those two readings. Because both of those readings have error in them, and we will talk about discuss how to treat the error in a reading like that, and how to, if you subtract one reading from another, for instance, how to handle the error in both of those numbers. So systematic errors are some things you can account for if you can find out what they are. 3 millimeters on a meter stick, 2 psi on my gauge. If you have a panel meter that doesn't read 0 and you can't really adjust it, then you have to compensate for that by either adding or subtracting the amount by which it's off 0 and hope that the scale is linear. Okay, so systematic errors, if you can figure them out, you can compensate for them. You can add 2 psi, subtract 3 millimeters, whatever you need to do to make it read right. The other kind of error, which is one we want to focus on most, is a random error. And you can call this a plus or minus error. That is, you take a measurement and you get a certain number, and you take another measurement, the same measurement, and you get a slightly different number. And you do it again, you get a slightly different number. So those numbers should give you, if you take enough numbers and take an average, we'll talk about those in a bit, and you get the best value for that reading. So random errors, plus or minus errors, sometimes they read a little high, sometimes they read a little low, but they're supposed to be reading the same thing every time, but they don't, because of your ability or inability to read perfectly and the instrument that you're using to work perfectly. You're going to get some variation in the values. So we want to talk about those errors. So let's focus on our random error. It's the above or below error, and so we can average these out. We can average those out by taking a number of readings and hopefully get a better value than just the value that we read once. Let's say we have a measured value. Back in the good old days, perhaps you just write the measured value down and you're done. You've got the answer, you're done. But now we have these errors. So we want to figure out how to represent these errors and how to work with these errors. So I'm going to use the symbol delta, small delta, as the uncertainty or error. So this is going to be the error in a measured quantity. Getting back to the random error business, if you measure something, the best value to report is the average value. So this is the average value, plus or minus, because it's a random error, the uncertainty in this measured value, which we have to talk a lot about. So, in fact, if you want to include these in the discussion, the measured value of a quantity is equal to the best value, that's the average value, plus or minus the uncertainty due to the random errors, plus or minus, depending on the examples I mentioned about the meter stick and the tire gauge. One was plus and one was minus. It's the plus or minus uncertainty, and it's a systematic error. This is what we need to talk about. You've done a lot of measuring of errors, and if you had some physics labs, and you probably know that the average value is the best value to report, and but you didn't spend much time talking about the error in that value. Before we get any further into this, I'd like to mention define another word. Deviation means the difference between two numbers, and in particular, the concept of maximum deviation. Let's take a look at an example. I'm going to write down 6 things, fixed measurements that I've made up here. 7.2, 7.4, 6.9, 6.8, 7.0, and 6.7. Okay, so I make these 6 measurements to 2 significant figures, and I want to add those all up and average them. And if I do that, you get 7.0. These average to exactly 7.0 to the 10th place. I write it this way, not just 7, because I did make these measurements to the 10th place, the 10th decimal place, and I want to make sure that I don't lose some information. There are some discussions about the more you average numbers, the more significant figures you can write out. We'll talk about significant figures later. But unless you write out a whole lot of numbers, take a lot of measurements, and they're very close together, you really can't eke out another significant figure. So we're stuck with the 10th place. What is the maximum deviation? Well, this is not a complete statement. The maximum deviation from the mean. The mean, the average, same thing. We're going to call it the same thing. Statisticians might disagree with that. But so the maximum deviation from the mean, if you look at these numbers, and you probably already have the answer. What is the maximum deviation from the mean? Which number is as far from the mean as any of the numbers in this list? And it's this number here, which is 0.4 above 7.0. So the maximum deviation is 0.4. Now, if you look at the maximum deviation below the average, it would be 0.3, but the maximum deviation means the value that's either highest above or lowest below the average. So we're done. The maximum deviation is 0.4, not 0.3 in this case. So I can write down, if I want to talk about the error range in this value, I can write down the answer is 7.0 plus or minus 0.4, because these numbers are obviously show a random error. Some numbers are above 7.0 and some numbers are below 7.0, and so pretty much evenly distributed. So here would be my reported value of the value plus or minus, because it's a random error, 0.4, which is the maximum deviation. That's kind of what you're stuck with when you only have 3 or 4 or 5 or maybe even 6 values like this. You can't do much more of a sophisticated error analysis than to report the range of values that is above and below your average value. So my x best here would be 7.0, which is the average, plus or minus 0.4. Now, if this is a bigger number, then these numbers are going to be spread out farther from 7.0 above and below 7.0. And if it's a smaller number, then obviously it says in a nutshell over there that your numbers here are really close together. For instance, if this is 0.1, then all these numbers are going to be between 6.9 and 7.1. So this says a lot about this distribution of numbers already. Okay, let's take a look at what's called the standard deviation. This is a lot more sophisticated and a little more complicated mathematically. And we generally describe that with the Greek symbol sigma. And you probably have heard about this if you had some math courses in which you do some statistics. So let's say this is the average value of some quantity, and I take a bunch of measurements like we did before. This might be 7.0, and this might be 7.4, and this might be 6.6. And I have lots of measurements, and if I plot the number of measurements versus the measurement itself, I do this for not just 6 readings, but 1,000 readings, I'm going to get a distribution of readings that are either closer to or farther from the average value. And that distribution, if I take 1,000 or thousands or 1,000,000 readings, is going to look something like this. Okay, this doesn't go to 0. It asymptotically approaches 0. Okay, so same over here. So this is a Gaussian distribution, and the maximum value, which I didn't quite hit here, is the average value, 7.0 in our case here. So I've got some, as I take more and more readings, I'm going to get a few that are actually above 7.4 and a few that are below 6.6. But most of them are going to continue to fill out this distribution. So this is a distribution of the measurements, the values of the measurement that you made. Now, the maximum deviation, of course, would be way out here someplace, and the maximum deviation we saw was +4 and -4. If I took, instead of 6 readings, I took 10 or 20 or 50 readings, I might get some numbers out here, but they're on the tail end of this distribution. So what the statistics show is that 68% of the readings that you're going to get, if you take millions and millions of readings, you'll find that 68% of the readings are between the average value and the average value plus sigma and the average value minus sigma. By the way, this x bar is just an easy way to say average. at least for me. There's lots of conventions about uncertainties, and I must say that in some ways they are themselves a little bit uncertain. But I'm going to use the ones that I like in terms of reporting errors and uncertainties. Okay, so 68% of the values fall between the standard deviation below and above the average value. So this is a little more refined, and obviously it takes a lot more readings than maybe 6 or so to come up with this distribution function that shows the Gaussian distribution of numbers that you're going to get when you try to measure something that averages 7.0. There is a formula for figuring out the standard deviation. This is not a math class, so I won't not go into this, but the standard deviation for the variable x is given by the following expression. It's the square root of the sum. This, by the way, this symbol here is big sigma. That's little sigma, capital sigma, and it stands for summation. Here's the way I want to write this, and I'll explain this in a bit here. X bar, you know, is the average value. X sub I is the individual value. We had on the board a bit ago 6 individual values. They would be 6.9, 7.3, whatever those 6 values we had. Divided by, and this is called the sample standard deviation, n minus 1, where n is the number of readings that you take. So n minus 1 in the case that I mentioned earlier would be 6 minus 1, or 5. To represent what this looks like, sigma x is equal to the square root of, let me just write out one of the terms, the sum of 7.2 minus 7.0 squared, plus the next term, the next reading was 7.4 minus 7.0 squared, and so forth for the 6 terms, divided by, I know this is kind of tedious, but you won't have to do it a lot, divided by 5, 6 minus 1, and the square root of that. So if you do that for that particular distribution, square these, add them all up, all 6 terms, divide by 5, take the square root, that should follow this theoretical curve. You're going to get 0.2, so plus or minus 0.2. So my measured value is the best value, which is the average value, plus or minus 0.2. And of course, this is less than 0.4. It's half of 0.4. Well, we don't have a lot of numbers here, so it's not going to work out that it's, this is about 2/3. It's not going to work out that it's 2/3 of 4. I guess 2/3 of 4 would round to 0.4 would round to 0.3. But this is what you get when you do this process. It says that the standard deviation, which is a much more refined look at the whole picture, is going to be plus or minus 7.0, plus or minus 0.2. Well, keep this in mind. This is a very handy formula for standard deviation. When you have, I would say, the borderline to me is 6. 6 or more readings. If you take 2 or 3 or 4 readings, then you can use the maximum deviation idea. And by the way, you should always take at least 3 readings of anything if you can, so that you get some idea of how dependable, how that number, how accurate that number is. Plus or minus 0.4 for 6 readings, and if you take more and more readings, you get a number closer to 2/3 of that value, which is probably more like 0.3 than 0.2. So now I'm going to go one layer deeper in this standard deviation business, because this standard deviation, this that we've been talking about here is the what's called the standard deviation of the distribution. It's the standard deviation. It says I got some points out here and some points out here. I got more values here than out here, and if I average them all, I get 7.0, and 2/3 of them roughly are between 6.8 and 7.2 according to this. That's the standard deviation of the distribution. But typically what we want, and what we just talked about what we want, is the average value. And so we want to talk about the standard deviation of the average. And again, there's a lot of mathematics involved here, but this is a simpler formula, and it's easy to get once you get this, because you know how many readings you took, and you know what the standard deviation of the distribution is. You're expecting to find 2/3 of those values within sigma plus and sigma minus of the average value. If you want to find the standard deviation, the standard deviation of the mean, that's what the x bar stands for. This is going to turn out to be the standard deviation of the distribution divided by the square root of the number of readings you took, which is, in the case we talked about earlier, which is 6. Square root of 6 is, well, it's between 2 and 3. So I forget which it rounds to 2 or 3. So this standard deviation of the mean is going to be smaller. If sigma sub x was 0.4, or 0.2 I should say, which it was, then sigma x bar is going to be about 0.1, a little bit less than 0.1 perhaps. But this is a little bit more than 0.2 actually. So that means that your values, the average value, 7.0, and if the standard deviation of the mean is going to be 0.1, that means that the number is a little more accurate than the standard deviation of the distribution, but it's going to be plus 7.0 plus or minus, I'm just saying, making this up, I haven't done the calculations, 0.1. And that's what you should report, because yes, we're typically interested in the mean value, the average value. That's the best value to use, and it's the value we're going to use to do our calculations and do the error analysis on the calculations for the answer. So deviation, maximum deviation, standard deviation of the mean, which is the best way to look at this if possible. So if you take more than 5 or 6 readings, you can always do a standard deviation and standard deviation of the mean calculation. They're not as accurate with only several readings as they are when you take 10 or 20 readings or 100 readings. The more readings you take, the more these data will fit that theoretical distribution curve, that Gaussian curve.